100% achieve question. What we have covered here. Any object, when you're describing it as performing simple harmonic motion, make sure you're able to explain these two things. Okay. Next is acceleration. Thank you, Mr. Kal. Now, I'm not going to visit this topic as if you are hearing it for the first time, because a lot of things you have covered already in the class. So sometimes, wherever there's some point I need to emphasize, I'm going to jump in. If we have to calculate maximum acceleration, what is the equation we use in simple harmonic motion related to this? K is, what is K in reality? Omega squared. Square of angular frequency. Okay, maximum acceleration is omega squared. I won't write it y there, but y becomes capital A. And what am I representing capital A for? Capital A is amplitude. Maximum displacement from equilibrium position. Omega squared A. That's how we calculate this. Now, around this equation, there's a very important graph to remember, which as such is not covered in the text, but it is covered, I think, in one of the exercises, if I'm not wrong, on used to be there. I don't know whether the new version has removed it. It's gone. That graph has been removed from the book, but quite an important graph. No, it's there. On page 166, exercise 10C, last question. Graph of negative amplitude, positive amplitude, and on this side you have acceleration, negative acceleration. It's a straight line graph which shows acceleration is directly proportional to displacement, which is what I started with, but what does it become equal to? The gradient of this line, and the gradient of this line is omega squared. Okay, now if acceleration, displacement is going this way, acceleration is coming this way, that's what the negative sign is for. So I have covered three main concepts there. A, what is simple harmonic motion? B, how to calculate maximum acceleration, and the graph. Okay, and this may not be that quite likely, but sometimes could be. These two are 100% questions. Usually there are questions around these two concepts. Okay, next, that's what I have covered just. Yes, this one. I hope my pace is okay for you to follow. So I can't afford to go too slow. I'm trying not to go too fast as well. This is the pendulum, equilibrium position, and this is its maximum displacement on either of the sides. Okay, what is velocity here? Velocity at equilibrium is maximum. Okay, V is maximum. What about V here? It was going this way, but here, because the velocity for a tiny fraction of a second, velocity becomes 0. So it turns back. The reason it is turning back is there is acceleration pointing towards this end, And this acceleration is causing restoring force. And we'll talk about this restoring force in few slides later, where it comes from and how to understand this restoring force. But the source of this restoring force is acceleration that is pointing towards equilibrium. So that's what the cause of restoring force is. While velocity is 0 at extremes, in the middle it's maximum. In here, there is some velocity, okay? Now because velocity is maximum here, what is happening as the pendulum is at this point, swinging, under ideal condition, there is no energy loss. Energy is just changing from one form to another. Okay, what form of energy is at extreme end? Potential, because it has gained certain height. So potential energy due to height, which is gravitational potential energy. Okay, in between here, it has kinetic as well as potential energy. What about right in the middle? It has come to equilibrium position, no height gain. Potential has become 0 now. All the energy is kinetic energy maximum. And given the V explains that, because what is kinetic energy? Half mv squared. This is maximum, so naturally kinetic energy is maximum. So the kinetic energy keeps on changing back and forth. Okay, now along with this, just here, I might be revisiting that later, but no, I think I'll visit it later once I do the reference circle. But at present, just remember velocity, kinetic energy, potential energy, and let's talk about acceleration as well. Which point acceleration is 0 and where is acceleration maximum? Where is acceleration maximum? Maximum displacement. Acceleration maximum here, and here no displacement, so acceleration is 0. Okay? And I've already covered how is maximum acceleration calculated. Minus omega squared a. How is maximum velocity calculated? What's the relationship between linear velocity and angular velocity? V equals r omega. Yes? And what is r here? R is a, which is the maximum displacement. So maximum velocity is a omega. Again, about this one and the other one, quite important things. They do ask questions around this. Calculate maximum velocity or calculate maximum acceleration. This equation is not given. The only equation given is this. But you should be able to relate R to amplitude. And that's what I have tried to show on that thing there, which is in terms of a spring now. Now I was explaining you with the pendulum. In spring what is happening? Going up and down. So at what's happening? Okay. This was the equilibrium position for the spring. So here velocity is maximum, acceleration is 0. Acceleration acting downward, but that's the maximum amplitude. So acceleration at these points and at this point, acceleration is maximum, but V is becoming 0. These are the maximum amplitude on the extended side, and this is on the compressed side. So So that is in case of spring. Another difference, here we are dealing with gravitational potential energy. There we are dealing with kinetic and elastic potential energy because of elasticity of the spring. Clear? Next, on reference circle, how should we show the position of the thing on the reference circle when it is pendulum and when it is spring? I would say draw the diagram something like this. You have a pendulum. Okay. And make sure on the thing next to it, you draw the reference circle as if this was the place where pendulum was going back and forth. Okay, when pendulum is here, which is this place, on this reference circle, show that position here. So the phasor for that on the reference circle is there. Now most of the books, as well as kind of the question, the way it goes in the NZQA, they prefer to go anti-clockwise. Okay. Now the pendulum has come here. What has happened on the reference circle when the pendulum has come there? What angle it has covered? This much of an angle it has covered. Okay. What about when the pendulum has just started from here, but instead of reaching that point, it is here. It has just come somewhere here. On the reference circle, how do we draw that? So what do? Bring the line straight down to the reference circle. That's where you are on the reference circle. And how do we show the angle? Come from there. That's the angle coming. Okay. Now suppose you have gone all the way this place and come back maybe here. So how much is the angle covered in terms of starting position? So first thing is mark out that on the reference circle. You know, now you have already gone through this point. So this line is not going to come down, but it is actually going to go up now. Okay, because this passage is already being covered. So you go up from here, that point, that's where you are on the reference circle. What's the angle now? So what you do, draw the line from here. Angle covered is all of this. So you work out this angle, which is 90 degrees, and the remaining you work out from that triangle. Because you would know this distance. You would know this distance as an amplitude. You can work out this angle theta. Angle theta is adjacent over hypotenuse. Clear? Okay. So that's how we use reference circle for the pendulum. When it covers full cycle, so when pendulum was here, that's where you are. When pendulum has come back to this place, that's where you are on the reference circle. When it has come to this point, that's where you are. Now suppose it has come back that place, it's somewhere there. You come down and your angle is this. All of that angle is covered. We will be doing some questions on this. And back again. So that completes one full cycle. Do you get this? This is the hardest bit in simple harmonic motion to visualize, as you can see on that one also. But that's with the spring. And I'll explain you with the spring how to do it. With the pendulum, I would say start from the bottom. It's easier to apply. And then go this way. Okay. When you're doing same thing on a spring, This is what it is, spring. Equilibrium position. So when you draw the circle for the spring, you do it that's where you are at equilibrium position. Start from here, because the spring is going to go back and forth in this direction, up and down. So starting equilibrium, you start from here. Okay, now the spring is compressed. Spring is compressed and the spring has actually gone till there. Where are you on the reference circle? In order to decide that, go here, and angle covered is this. Now the spring has gone up here, that's the maximum displacement. On the reference circle, you have covered this point. Spring starts coming down and spring has reached here. Where are you on the reference circle? So you move on the reference circle and see where that thing is. That's where you are. So in reality, the angle covered starting from here is this. So spring, preferably start from here and then you go this way. You're going up and down on this line, but when you're doing this, you go across this line back and forth. Start from here and then go this way. Does that make sense? Yep. Next. That's what is happening with the spring. That's with the pendulum. And I don't know whether in your class that activity was covered outside with the chalk and circles, walking across. A lot of people did manage to get good understanding of reference circle with this. This is more applicable to spring going up and down on the reference circle. Now this one, quite complex the way it looks here, but I am going to show you an easier version of that. Pendulum. Displacement here, how much? 0. Velocity, maximum. Acceleration, 0. What about this point here? Displacement, maybe A. Acceleration, directly proportional to A, but negative. Okay? Or acceleration is going to be minus omega squared A, which is directly related. Velocity is 0. So what is happening? At equilibrium, velocity is maximum, displacement is 0. So on the reference circle for the pendulum, if I have to show a displacement phasor, you all are familiar with phasor word now. You have covered it in this topic, you have covered it in AC circuit as well. Okay, so if I have to show displacement phasor at time t equals 0, I'm going to use this axis for 3 things: velocity, acceleration, as well as for displacement. Okay, displacement at time t equals 0, this is the time, t equals 0 here, displacement is 0. What's happening to the displacement as I'm going further? Displacement is increasing. I'm here, maximum point, that's where I am on the thing. Now I am going back here, which is I'm coming towards equilibrium, towards 0 point, and now I'm going back there and here. So what's happening on this side? That's my displacement phasor. Can you all get that? How am I drawing displacement y with time? So orange is showing y, because I don't want to label this x as this y, can be used for acceleration as well as for v. If I have to show now velocity on here, what is velocity at equilibrium? Maximum. And where should I start maximum velocity at t equals 0? Here. Yes. And then comes down and then goes up again. When that one is maximum, this one is 0. When that one is 0, this one is maximum. So that means velocity is always ahead of displacement phasor by 90 degrees. So if I draw on the reference circle, that's my displacement phasor. Velocity phasor is that. What about acceleration? Acceleration at equilibrium is also 0. But acceleration is always acting opposite to displacement. So on my graph, acceleration is going to be this way. Like that. The value might be slightly different from the actual acceleration because it is multiplied with the omega squared. So where is my acceleration phasor? Out of phase from displacement by 180 degrees. Do you get this? Yep. Not covered in the book again, but recently they have been started coming back to this topic. And it should be easier to visualize this if you have understood phases well in AC topic. So far, how do you feel? Okay? That's what is happening in this diagram. Different colors are representing different things. So can you tell me what is blue line showing? If blue is displacement, what is green? Velocity, and orange is acceleration. Blue if you're using for displacement, then orange is for acceleration, green is for velocity. Does that make sense now? Yeah? I won't cover this right now. Not now. Okay. I'll come back to these ones later. Are you still lost with this? Yeah?
Your drawing up there is slightly different from the one up there. Is it a black line, I think? Or is it just me? I can't tell.
Black line is the time.
The black line here, is that the acceleration, right?
Yeah.
But then on there, if you use the blue line for displacement, isn't it the orange line for acceleration?
Yeah, it's only thing they haven't started right from the beginning. They should have started it from 0.
Okay.
Yeah. It's not, orange is not going to mean correctly, perfectly right. It's kind of like that.
So it's kind of like that.
That kind of like that. Yeah, I've got the old book, I can show you from there. Yeah. Yes, Jordan? Sorry, Jordine?
How come from the diagram none of them are leading by 90?
That one is wrong. Mine is right. Yeah. Okay. Next is Are you guys okay with deriving these ones? Y equals A sine omega t. V equals A omega cos omega t. And acceleration is minus A omega squared sine omega t. Then there is y is A cos omega t. V is A omega sine omega t. And have you seen these before? Yes. Now do you want me to go in depth into these equations? How do they come from? Where do they come from? No? Not really? Everyone happy? Yes? Negative A omega or I can put y there. Okay. In fact, it will be better if I put what is the used in the book? They have used A. Y is A sine omega t, and then I use A omega squared. Happy? Now, what I really want you to do here is, on page 161, page 162 and 63, their explanation with the vectors is given. Quite recently, they have started getting into these vector related questions. Which way is the velocity acting? Those kind of stuff. If you do not have an understanding of those, can you please make sure by end of today's session get that sorted? Because you said you don't want to get into this, so I'm not doing that. But there are 3 circles given, and on that can you see those vectors? Especially on page 163, the 162, can you see A omega and V in a shaded triangle? And then there is another shaded triangle, A omega squared and A. You should have a good understanding of those 2 triangles. Clear? Any questions so far? Any question? No question? Yes? Yes, that's my question. What is the difference between top 3 and bottom 3? There is a situation when you use top 3, and there is a situation when we use bottom 3. If time counting starts from equilibrium position, we use these equations. When the time counting starts from the maximum displacement, either end, we use these equations. That's quite critical, because otherwise we are going to get wrong answer. So that decision making, it's up to you. All 6 equations are given in the paper, but you have to decide when to use which one. Yes?
Can you just repeat it again?
These 3 are used when at t equals 0, object is at equilibrium. And the bottom 3 we use at t equals 0, object is at maximum displacement. Okay, that's the difference between the two. Now if we look at either these two or these two, I can break this equation as y is a sine omega t and the other one is a omega squared sine omega t. The only thing different here from there is omega. So I can substitute this whole thing here, and what will my equation be? A omega squared. Sorry, omega squared y, not a. Omega squared y. Because I'm replacing this, if I write it like this, minus omega squared a sine omega t. And what is this a sine omega t is? Y from there. Does that make sense? And we go back to the same basic of simple harmonic motion. Acceleration is directly proportional to displacement. Constant of proportionality, angular frequency squared. Negative sign because the two are opposite to each other. And if you fail to catch up any of these in your book, page 153, there are 4 bullets given. Essential features of simple harmonic motion. This is definitely going to help you for something on explanatory questions. Fine here, guys? Okay, the next thing is time period. Time period in simple harmonic motion. You will be focusing on based on 2 things. Time period of a spring and time period of a pendulum. Equation for the spring is 2 pi square root mass over k. Time is only dependent on 2 things: the mass that is hanging on the spring and the stiffness of the spring. You make it a stiffer spring, time period will reduce. Inversely related. Increase the mass, time period will increase. Directly related. Okay, deriving of the equation very easily, it's given on the book. I am not explaining you that, but if anybody is stuck, I don't know how to do it, page 100 and, yep, no problem, where did I put my glasses? Page 168. And page 170 gives you time period for the pendulum, 2 pi square root L over G, and there is a mistake on that page. They've done G over L. That's not right. L over G, directly proportional to the length of the pendulum, inversely related to the gravity. Again, deriving of that equation, which could be kind of ends or ease end. If you cannot understand page 170, I'm more than happy to explain you later. Okay. Next bit. question.
Yeah.
Yeah.
So the top one is for the string and is the bottom one for
Pendulum. Length of the pendulum. Longer the pendulum, bigger the time period is going to be. Have you guys been ever on a swing?
Everyone what?
Swing.
Oh yeah.
Okay. Have you tried swing standing and sitting? Have you ever tried on a swing in a standing position? Okay, and in a sitting position. Which one is going to increase the period of swing? Sitting or standing? Sitting. Why? Center of mass is lower in sitting position, so length increases. While standing, center of mass of your body is a bit higher, so the length is relatively only till the center of mass. Nothing beyond that, we are not interested. Legs, yes, they do have some mass, but we concentrate mass only in the position where the gravity is acting. So the length is a little smaller, while standing, time period is going to be smaller. And while sitting, time period is going to be more. Good understanding there. That's physics. Next one on kinetic energies in the pendulum. If it's a spring, what are the two energies? Elastic potential energy and kinetic energy, yes? Do you remember Hooke's law from last year? Do you remember Hooke's law from last year? What was Hooke's law? F equals kx. Okay, now for our convenience, x we are going to replace it by ky. We will be calling y as a displacement rather than x. So when the displacement is y for the spring that was here, and now the spring is extended right till there, that was the spring hanging. So instead of this equilibrium position, it has come from that equilibrium to this point. What has happened? It has stretched. Elastic potential energy is there. How much energy is stored in the spring now? Hooke's law. The graph, underneath the graph is the energy, and the equation was half k y squared, but now y is the maximum displacement, which is amplitude, so we will call it as half ka squared. That's the elastic potential energy at this extreme and maybe at this extreme. Half ka squared. Anywhere in between, if you are working out EP is still there in between, but that EP is going to be half ky squared. Whatever the displacement y is from the equilibrium position, that's what the elastic potential energy is. But then remember, in between, it also has kinetic energy. If you have been given the mass of the spring, mass hanging on the spring, the displacement and the maximum amplitude, you can work out speed at which it is going up and down. Because what's happening, what's kinetic energy? Kinetic energy is half mv squared. EP at extreme or at maximum extension is half ka squared. We can calculate that. Okay, now in between here, what is happening? It is some of them is EP, some of them is EK. EP is half ky squared plus how much is EK is half mv squared, mass is known, and we also know the total energy is Ka squared. Because under real situation we are ignoring any energy loss. Energy is just changing from one form to another. So total anywhere is going to be Ka squared. If you've been asked, work out the total energy at this point, and you will say, no, I can't, I don't know the velocity. You knew the amplitude, you knew the spring constant, whatever energy is there, that's the total here, that's the total here as well. Total energy stays constant, and that's what you have in something in your book. Total energy is constant. So if I take that as my negative amplitude, that as my positive amplitude. Now at these points, if I draw this, and that's my equilibrium, zero position. Which energy am I showing with this line? At zero, which energy is maximum? At equilibrium, which energy am I showing in this graph? Kinetic or potential? Kinetic. This black line is Ek. Ek is zero here. And if I have to show potential, which is going to be opposite of that. Maximum here, zero there. Maximum there, zero here. Does that make sense? Yes? Another important graph. Another one is, during one full cycle, what happens to the energy if I do it this one, half a cycle, full cycle? During each cycle, 2 times potential energy if I start this at equilibrium, maximum, then becoming zero, then maximum becoming zero. This is equilibrium, went to extreme, equilibrium, extreme here. So if I do the pendulum, this point, EP was zero, EP has become maximum. That's what I'm showing there. Come back there, that's what it is. Now it has gone on to this side, that's where that is. Now it has come back full cycle. So twice it has become double. And if I have to draw on the same thing, EK will start from here, that, and that. Twice maximum and twice minimum here. Make sense? Okay. So that's with the energy part. Another important one that I wanted to cover with the energy part, which is not given in your book. Okay, you're fine with this part, half ky at any position, maximum this is half Ka squared. What about Ek? Ek at any point is half mv squared, but what about maximum Ek, if we have to calculate straight from there? V is R omega, fine, which is same as A omega. So instead of V, I can substitute maximum velocity, because we know at maximum velocity energy is only kinetic. So what will the equation will become? Half m A omega whole square is ek max, which is half m A square omega square. That's the equation. Two more things in theory I need to cover. One is damping and resonance. We're going all good. My target was in 1 hour finish everything and then focus on some past papers. Damping graph, easy. With time, and what's on this axis? Amplitude. So if you start like this, with time the amplitude is decreasing. That's what the damping graph is. The reason it is decreasing, it's losing its energy to the outer environment, which would be due to air resistance. Okay, and I can't remember which year. One of the year, around this, very easy, excellence question was there, around damping. But still, quite a favorite part to ask in question. And the last bit is resonance graph. What are the two things in the resonance graph? We're not talking about AC circuit here. We are with the simple harmonic motion. Frequency against amplitude. That's the graph. This is the resonance frequency. At resonance frequency, amplitude is maximum. Can anybody explain this? Why is amplitude maximum at resonance frequency? Now this has got nothing to do with inductor and capacitor. Okay. Now this frequency here is external driving frequency. Okay. You all must have heard either about breaking of glass with the music, or to my classes I did show them the bridge that had collapsed in States in 1940s. Okay, now what had happened that time? The external driving frequency is the wind blowing. Okay, because of the wind, the bridge starts swinging. Now every object, including us, we have our natural frequency. If somebody derive around us an external frequency that would match our natural frequency, we would be blown apart into pieces. Okay, so that's what is happening, because our body will swing with that frequency. The moment that frequency matches our natural frequency, our amplitude will be so big that we will be shattered into pieces. That's what is being shown in this graph. Moving further, I will cover this when I'm doing one of the past paper, but this concept is really, really good even for scholarship students. All of this. It's mainly at excellence and merit levels. So if you are aiming just for an achieve, please ignore it. Now let's move on to the past papers. Here. Can you all read that? You might have seen this question before. Daniel is having fun on a swing. Yes, he is indeed. He lifts his feet without pushing his swing out over the river in simple harmonic motion. So that's where the river is. And the angular frequency is 1.45 radians per second. First thing, as a physicist, you should sort out what are these quantities. What symbol am I supposed to write in front of this? Omega, yes. Next, what is given? He travels a distance of 0.8 meter before reaching equilibrium. So what is 0.8 meters? A, sorted. Calculate the acceleration of Daniel's simple harmonic motion at instant he lifts his feet. What kind of acceleration is that? Now he is here. Equilibrium position is somewhere there. Okay. The moment he lifts his feet, what is acceleration here? Maximum, minimum, maximum, because it is at maximum displacement. So acceleration is omega squared A. Fine, both the things are given. Fill them. It's easy achieved there. Fine with that question. Next question is, calculates the distance Daniel travels in 1.8 seconds after he lifts his feet. 1.8 seconds is easy time. And what do we have to calculate? What symbol should I put? Pardon? Y. We have to work out this. And which is the equation we are going to pick now? Which equation are we going to pick for this? Out of the various equations we have seen today. Y equals A sine. What next? Omega t. What made you choose this position, this equation? T is at maximum displacement. We will not use that equation. We will use this equation. A cos omega t. At time t equals 0, he is at maximum displacement. So we will use cos equation, not the sine equation. Get it? Lawrence, what's the problem? I think you have a question.
Did you say we use sine?
Now we use cos. People told me to write sine, so I wrote sine. And another important thing to remember while working with this. What's the most important thing to remember? Because you're going to put all this into your calculator, and calculator should be in radian mode. Okay, come on, do it. I want you to do this question. You think it's easy. It's not that easy. Still, it is not easy. It's an excellent question. Let me tell you. Calculation, please, everyone. Justin, no discussion. Do the calculation, please. answer, guys? Y is negative 0.69 unit meters. You're happy with that? You're happy? If you leave it just there, you're getting, I think, achieve. But it's an excellence question. Because you're getting your answer in negative, it has covered this distance, and if you're counting that distance as positive, it has gone further than that, and that distance is negative. 0.69 is just this what you have calculated, but this one is still missing. So you need to add this remaining distance with it. And how much is the answer then? So you will have 0.69 plus 0.8, and that gives you the answer 1.49 meters, and that's the correct distance. So you're not just covering this much, you're covering whole of that in 1.8 seconds, and that's what takes you to E. So because the answer was coming negative, someone of you might think, oh, I think I made some mistake. No, you have gone beyond equilibrium position, which is fine, but then you take into account this. Do you get this? Yep. Next. On.
Because when they go like there and they're active,
Yeah.
you can't calculate the displacement or the displacement. But y is displacement.
Y is displacement, yeah. On another occasion, Daniel travels in, instead of lifting his feet, Daniel pushes off from the starting point. Discuss what effect this could have on motion of his swing. Your answer should include an explanation for why the amplitude of his swing increases. So what's the answer here? We're doing really good. We might be managing before 5:20. Okay guys, now he's adding some more energy from his end. It is not just the energy that was originally due to the height of that swing. Okay, there's an extra energy added by him now. So naturally, when he starts, he's not starting with 0 velocity. He has some initial velocity there because he's added some extra energy and force into it. So he's starting with some kinetic energy. So naturally that kinetic energy, by the time he reaches that equilibrium position, A is going to take him more lower position than that, and plus when he's coming up this way, he has more kinetic energy at this point. So what's happening, if normally he would have stopped here, he's changed all the kinetic energy into potential, but because now in comparison to the previous situation, he has more kinetic energy, that is going to take him to a bigger amplitude before it all changes to potential energy. So the amplitude gets bigger. Now, ideally, it was just potential kinetic changing on its own, but here he is adding extra energy. So this motion is not just that same amplitude remaining, amplitude is increasing beyond the actual amplitude. It is no more simple harmonic motion. Okay, simple harmonic motion was happening only because of this restoring force that is pulling it back to the equilibrium. But here, it's his extra own force as well, not just the restoring force. So that is making it not simple harmonic and making the amplitude bigger. You have to explain all that stuff. A in terms of acceleration is directly proportional to displacement. Here displacement is increasing not because of the restoring force, but it is because of his extra added force. Plus, at the start, kinetic energy is not 0. Kinetic energy, there is some initial kinetic energy which is adding into this kinetic energy. More kinetic energy is taking him to a bigger amplitude. Need to explain all of that, and that's an excellence question, explanation. And I think we have covered the last one already. Sitting and standing on the swing. Yep.
Why is it lower?
Pardon?
Why is it he goes lower? From that?
He's having more kinetic energy.
Yeah.
So that's going to take him a little bit more deeper into the swing. Next part. Do you want to do the next question? I think the reference circle question we will do it here, and after that we will call it off. No, C is also important. I think we'll do till we'll finish this question. Okay. Read the question from the top. Brad is working on a scaffold. It is two numbers given, 5.5 and 0.9 meters. What are these? What is 5.5? No worries. What's 5.5? L. And what is 0.9? amplitude. Okay, next, show that the time period of backswing is 4.7. Easy. Just substitute everything in here. We won't spend time on this. L over G, and then get the value as 4.7. That was a difficult one. Calculate the maximum velocity of the swinging bag. What's the equation for maximum velocity? V equals V max is A omega. I know A, I don't know this. How do I do that? How do I get omega? Omega is theta over T. But what is theta? Full cycle. 2 pi, 1 full cycle. And for 1 full cycle, what is T? 2 pi over T. I know T, so I can work out omega. Yes? Omega is 2 pi over T. So from that, you work out omega and then substitute in there. Now to save time, I am just going to give you the value of omega because we might need that later. 1.337 radians per second. Show on the diagram where his maximum velocity occurs. Easy? Is there anyone who finds this difficult to show on the drawing where his maximum velocity is? 1, 2, 3. So wait. 2. Yes. Explain how the tension in the rope varies as bag swings. The tension is here. Okay, that cord is causing the tension. How the tension is changing as the bag is swinging. Now this is the question which was quite a challenging one in that particular year. I know this was the year my daughter was in year 13 and it was a scholarship question actually. And in order to do that, now I'm going to take you back to these things here. From this point, from the current slide. What do you see with the tension force there? Just look at the size. What's happening to the tension force? Here, smallest, bigger, highest here, same as that one, least there. Okay, that's one thing to understand. Okay, tension is highest at the end, smallest at the end, biggest here. The reason for that is, now this tension at this point and this point is going to give some kind of centripetal force as well. Okay, but remember, this concept is simple pendulum. It's not conical pendulum of the previous topic. Okay, here velocity is maximum. We all agree. What is centripetal force? Centripetal force is Fc is mv squared over r. If velocity is maximum, that means centripetal force is maximum there. But centripetal force here and these points is 0. As it keeps on coming towards this end, there's some centripetal force. Okay. Another thing to remember here is restoring force. The restoring force is not centripetal force. Please remember that. I said centripetal force is 0 there, but that's not the case with the restoring force. Restoring force was maximum at the extremes and minimum in the middle. Okay, 0 in the middle. So let's look at the source of restoring force. Any guess, where is restoring force coming from? From this component, gravity. The weight force is contributing to the restoring force. And how is that? Let's look at this. The gravity is resolved into two components. The vertical one is in line with the tension force here, and that one is acting inward. That's what the restoring force is. Okay. So as you can see, as it is coming inner, restoring is becoming smaller, and this component is kind of getting slightly bigger. At this point, tension is getting bigger, and it's almost balancing the whole thing with the gravity. Gravity does not have any horizontal component there. Okay, that's totally being balanced by the tension force, as you can see here. This one is a little bit misleading, but I think the previous one is better. I don't think there's any more after this yet. So just this two. So tension force is maximum in the middle, and it is in straight line with the gravity as such, not with the vertical component of the gravity. There's no horizontal component of the gravity in the middle, but the horizontal component at the extremes and in between position are contributing to the restoring force. So this is all you are writing. Plus, you're also mentioning about tension force in the middle. There is maximum velocity, so there's going to be maximum centripetal force acting towards the center, okay, which is coming from the tension force, whereas the centripetal force at the end is 0, velocity is 0. And again, if you want to read about this more in detail, go on to the website Physics Classroom and look for oscillations in simple pendulum or pendulum oscillations. Physics Classroom, that explains this part again. Okay, was quite a difficult question. Now going back onto this question. How the tension in the rope varies in bag swings. How the maximum velocity of the bag would change if Brad had used a longer rope to attach his bag to hook 2. Okay, this is a good question. How the maximum velocity would change if he used a longer rope. What is velocity dependent on? A omega. Yeah? So it is, if omega is changing, if that's increasing, this one will increase. If omega decreases, that one will decrease. But what is omega dependent on? 2 pi over t. Yes? And what is t dependent on? 2 pi square root L over G. And what they are saying, you are increasing the length. So what will happen to t? T will increase. T will increase here. What happens here? Decreases. What happens to the velocity if that one is decreasing? How many equations you are using to explain? 3. And it was a merit question. Okay? Last one that I wanted to cover here, that's what the reference circle question is. This one. Brad offered his friend Anne a sandwich from his bag. He lets the bag swing when Anne is 1.4 meters away. He calls to her when the bag has traveled 0.1 meter. Anne's reaction time is 0.4 seconds. Calculate the time between Brad's call and when the bag reaches Anne. Use the reference circle. Who will draw the diagram on the reference circle? How much is this distance? 0.9 meters. And the distance from Brad to, he lets the bag swing when Anne is 1.4 meter away. So she is 0.9, 0.9, 1.8. So this is kind of somewhere here. 1.4. Agree? Okay. Next, what is the another number we have to look very carefully? He calls Anne when the bag has already traveled 0.1 meter. That means it is somewhere here the bag is. When he says, hey Anne, food is coming. Make sure you catch the bag. Okay. So her reaction time is 0.4 seconds. If the bag is reaching more than in this time, then she will be able to catch it. If the bag is reaching less than this time, sorry, I didn't even hear you. So I was unable to catch it. So we have to work out the time taken to reach from this point to this point. And how do we do that? We'll have to use the reference circle. So go on from here to this point. That's where you are on the reference circle. So from equilibrium position, if I have to draw, its phasor is this point. Agree? That's where the phasor was when he called on the reference circle. Anne is here. So on the reference circle, it is this. Okay, this point. So where do I draw from the equilibrium? This. Agree? Now this is my middle point. It's better to draw that middle point because that's going to help us. You have to work out this angle. You have to work out this angle. And then you will work out the time taken to cover that much angular displacement. So for that, what do we need to do? Draw this triangle. And I very much know this distance. How much is this distance? Pardon? Louder? 0.9 is this. 0.8. Because minus this. 0.8. Everyone agree why this is 0.8? Because it's that distance I'm measuring here. Okay? Next. What is the distance this? How much is that distance? 0.5. Correct. Because this was whole thing 0.9 and this one was 1.4 from there. So you're left with 0.5. So how do I get theta there? Theta is sine theta or cos theta. Which sign do we have to use? Opposite over hypotenuse. Sine theta is opposite. And how much is hypotenuse? Amplitude 0.9. And another theta is sine theta 2. 1, 2 is 0.5 divided by 0.9. So can we work out theta 1 and theta 2? Yes? So, theta 1 is sine inverse 0.8 divided by 0.9 and theta 2 is, so total theta is sine inverse 0.5 divided by 0.9. Remember, radian mode. Answer, anyone. Let's see who's good in calculation.
1.68.
1 point, 1.68? Yeah, 1.68 radians. So our aim is not to work out the angle, we have to work out the time. How do we get time from here? Do you want to learn an easy way or difficult way? Easy way. Easy way is just this. Theta omega is theta over t. And what is t? Theta over omega. And we know omega 1.337. Yes? So, it's 1.68 divided by 1.337. How much is that time?
$1.26.
1.26 seconds. And if you want to do it on a difficult side, then it is going to be time taken to complete full cycle is 4.7. It's given, which is 2 pi radian. So how much is 1 radian? 2 pi radian are covered in 4.7 seconds. 1 radian will be covered in 4.7 divided by 2 pi seconds, and that many radians will be covered in 4.7 divided by 2 pi times 1.68. Either or, still you get the same answer. That's an easier way, that's a difficult way. Slightly difficult one. But it's better to have an understanding of both. Do you get how I get this? Yep. So that 1.2 second, will she able to catch the bag? Her reaction time was this. Easy as. No problem. And moreover, it's a sandwich. Food time. Let's go home now.
Oh, really?
Yeah, really.
So we
Oh, okay. Are you happy with this? Pardon? He has released the bag. What the question says is, read the question. Brad offers his friend Anna a sandwich. He lets the bag swing when Anne is 1.2. Okay. He calls to her when the bag has traveled. He's already released, but he calls her at this point when the bag is.
Let's try to turn this off.
Okay. Can you please put the chairs up? And can we turn that off?
Is the middle button?